Today we're talking about isotopes, and I'm showing a picture here of a human hand that has 6 fingers, because if you asked, and I'm counting thumbs as fingers, if you asked what's the average number of fingers on a human hand, somebody would probably say 5. Well, just for fun I made up this data. What if 6 million people had 5 fingers, 240,000 people had 4 fingers, and 1,800 people had 6 fingers? I said, again, no, I made this up. I'm sure there are also people who have no fingers, 1 finger, 2 fingers, etc. So, again, what's the average number of fingers on a human hand? You would have to take those percentages of how many fingers are abundant, and you would have to calculate it that way. It's the same thing with atoms. So, as just a review, every single atom of an element has the same number of protons. You can't change that. So every single carbon atom in the world has 6 protons. If it didn't have 6 protons, if it had 5 or 7 or 8, it would be a different element. However, atoms of the same element can have a different number of neutrons. Since mass is protons plus neutrons, these atoms have different mass numbers. But that doesn't mean that it's not still a carbon atom. So for example, we've got a carbon 12, a carbon 13, and a carbon 14. Carbon 12 is the most common. How do I know that? Because when I look at the periodic table, at the bottom of carbon square it says 12.011. So the average is pretty close to 12. But some carbon atoms have an extra neutron or 2 extra neutrons from the most common one. We call all of these isotopes. There are 3 isotopes of carbon. How do you measure the mass of a tiny atom? Well, again, they don't want to be saying that protons weigh 0.000000001 grams or something like that. So they call them atomic mass units. And they simplified it by saying that protons have a mass of 1, and neutrons also have a mass of 1. And they base this on carbon, so 1 atomic mass unit is 1/12 the mass of a carbon atom. By the way, that huge number of atomic mass units is equal to 1 pound. That is an enormous number. You'll often see elements written like this, where there's the symbol, and then there's like something in the upper left corner of the symbol and something in the lower left. You always write the mass number in the upper left corner and the atomic number in the lower left. So that's how you know what element it is. So this is the sodium atom that has 11 protons because its atomic number is number 11, and this particular atom has a mass of 23, which must mean that 23 minus 11, it has 12 neutrons, sorry. A lot of times you'll see them written too as something like sodium-23 or cobalt-60. So isotopes are named a lot of times by their mass number. So you try. How would you write the name and symbol for a neon atom that has 10 protons and 11 neutrons? Well, what would the mass be? 10 plus 11 makes 21, so you would put a 21 in the upper left corner. It's number 10, so the lower left corner would get a 10, and you would name it after its mass. So it would be neon-21. How about another example? What if an atom has 15 protons and 17 neutrons? 15 plus 17 is 32, so we would name it, it's number 15, so we would name it phosphorus-32. The 32 would go in the upper left corner, and the 15 would go in the lower left corner of the P. How about these questions about this particular symbol? How many protons does this copper have? 29, otherwise it wouldn't be copper. What is the mass number? The upper left corner, 63. How many neutrons does it have? 63 minus 29, 34. How do you calculate the average atomic mass? Well, you take the mass times the frequency of that mass occurring, otherwise known as the relative abundancy. And these weren't supposed to pop up yet, but for example, if the percent abundance is 59.2, the relative abundance would just be moving that decimal 2 back 0.592. If the percent abundance were 2.4%, again move the decimal 2 back 0.024. That's going to help us solve our problem. So for this first problem, this one's done for you. It says rubidium-85 and rubidium-87 have abundances of 72.2% and 27.8%. What does that mean? Well, it means that most of the time a rubidium atom weighs 85 AMU, but about a quarter of the time it weighs 87 because it must have 2 extra neutrons. So to calculate the average atomic mass, we take 85 times the relative abundance, 0.722. Again, I just got this number by moving the decimal 2 back from the percent abundance, and then add the other isotope's mass, 87, times 0.278. That comes out to be 85.56 AMU. Or the other optional units you could use for the periodic table are grams per mole, because that's how many grams 1 mole of rubidium atoms would weigh on average. Before I show the next screen, I want to encourage you, if you're filling in the blanks on your notes, that you go ahead and try to do that problem on your own and pause the video here. The next problem has 3 isotopes, and it's still done the same way, where you take each mass times the relative abundance and you add them all together. So the answer for that second problem should be 237.98. And then the last problem, what if you had a mystery element, but you knew it had 2 isotopes? How could you figure out what the atomic mass, average atomic mass would be? Well, you'd take 12 times 0.9889 plus 13.00335 times 0.0111. Once you've added those together, you should get 12.011. And that is the average atomic mass for carbon.